I'm going to talk about why we think that the sun has a large effect on climate and that it's going through cosmic rays. My talk is sort of divided into three parts. And the first part is some of the empirical evidence, which Nia already has been talking about, why we think that there is a connection between solar activity and climate. And the other thing is trying to understand what this microphysical link is, which I think is the most important part, that is trying to understand why cosmic rays seems to be connected to clouds and how it actually connects to climate. And then I'm going to say a few things about the long time scales, because it's simply an independent way of checking whether cosmic rays are important, even on these long time scales. So what you see here is actually the heliosphere. So in the middle, the yellow part here is supposed to be our sun, and the circle is actually 100 times larger than the distance from the sun to the Earth. But this is the region of space which is affected by the sun's magnetic field or the solar wind. And this is quite important because this is how solar activity can modulate the cosmic rays. The cosmic rays, they enter from the interstellar space. When large stars explode, then you have an acceleration of particles. And that means that in the interstellar space, you have a lot of very high energy particles moving around. And some of them, they enters into the solar system. And even fewer actually might end up in the top of our atmosphere. And if you have 100 GeV particle, you can see here that it enters and then it interacts with the atoms or the nucleus of the atmosphere, and you get this kind of shower structure all the way down through the atmosphere. And why this is important is because it ionizes the atmosphere, and the ions are extremely important in the story I'm going to tell, because it's really what helps produce it helps produce the aerosols, which are important for cloud formation. But another thing they do is that they produce all these isotopes, which I've just shown you a few here. One is carbon-14, which everybody knows from the archaeological, where you can use it to date organic material back in time. But it also is important because you can use it to figure out how solar activity varied back in time. So if we, for instance, look at one of these examples that show that there is a connection between solar activity and climate, what I'm showing you here is the last 1,000 years. And you see this reconstruction of climate where you have some variations. You have the Little Ice Age, you have the modern period here with the temperature going up. But if you compare it with the changes in cosmic rays, that is carbon-14, you get a result that looks something like this. And you see the very beautiful correlation between the two curves. And this is, of course, a very strong suggestion that there is a connection between solar activity and climate. And this has been the inspiration, of course, for many people and for many, many years that you find these kind of correlations. And Nia showed you that these correlations, they can be extended thousands of years back with respect to solar activity. Another thing you should notice is that the cosmic rays are actually increasing downwards. It means that when you have more cosmic rays, so this is this here, you actually have a colder climate, and vice versa. Fewer cosmic rays, you have a warmer climate. Now, you always talk about we'd also talked about the present-day climate, and here you see the radiosonde data. This is from 1958 to 2012. and it is over a large part of the atmosphere. And you see these, there's a lot of variation in the data when you look at such short time scales. But what I wanted to do is just to show you that even in these data sets here, there's a very clear solar signal. Of course, we know that there's the El Nino, and we have the cooling after the El Nino. We have the volcanic eruption, I think here in 91, Pinatubo. But if you then do a regression, that is somehow you remove these fluctuations and you look what is the residual after you move the volcanic and the El Nino, you get a result that looks something like this, where the blue curve, or the fluctuating curve here, is the change in temperature. The red curve is actually the change in cosmic rays, where we have taken out long-term trends. And you see the blue curve is actually the average of this temperature fluctuations. And you see this is a very beautiful correlation. And again, we are in a situation where the fluctuations are actually too large to be explained just by solar irradiance, which I will mention in a short period. Now, the question that we have all asked is why there is this correlation. I mean, why should there be an amplification, and what could amplify the solar signal? And it should become as no surprise, because this is what I've been working on for such a long time, is that we have used the clouds in order to understand what is going on. The cloud cover is, of course, extremely important for the radiative balance of the Earth. The net effect of clouds, I mean, they both heat the atmosphere and they cool the atmosphere, but the net effect is actually a cooling. So if we have more clouds, we should get a cooler temperature, so the temperature should go down. So the idea is that when we have more cosmic rays, we should have more clouds. And this curve I have also shown many times. This is a satellite observation from 1983 until 2006. It is showing in the blue curve that is the change in the low clouds over this period, and the red curve is a change in cosmic rays over the same period. So this was actually an inspiration for sort of the initial thing that started my research into this problem. We started around 1995 doing these things. However, this correlation, because of calibration problems, it actually breaks down, and you can no longer see such a beautiful correlations. And since then, new satellites has come up, but they're usually only single satellites, and single satellites are simply not sufficient to get these long-term trends, because it's very difficult to have a calibrated system. Nonetheless, if this reflects some truth, that we have these variations, then they are on the order of 1 to 2% changes in the cloud or low cloud cover. It means that the effect is on the order of 1 watt. What you see here is the graph that Nia showed you, where you see that the changes that you see in the ocean is on the order of 1 watt per square meter, and that the solar irradiance was a factor of 5 to 7 times too small to explain it. But with the clouds, we actually get an amplification factor that seems to be fitting very nicely with the observations. And I should say that it's not just from this curve that we have these variations. I will show you later that we can also see on short terms that we have a connection between cosmic rays and the cloud cover. So the obvious question is, why should cosmic rays affect clouds? And it turns out, that in order to have a cloud droplet, you have to have an aerosol in the Earth's atmosphere, because the water vapor needs a surface to condense on. And in order to condense on one of these aerosols, it has to have a certain size. So the air is actually filled with these very, very small particles, and you can't see them because they're simply too small. And it turns out a large fraction of them are actually produced directly in the atmosphere, where you have gases, where one of the most important molecules is actually sulfuric acid, that they condense into a cluster, and then the cluster slowly grows to cloud condensation nuclei, and then they can affect the cloud cover. And the idea that we have been working on is that the ionization by cosmic rays is actually helping stabilizing these small clusters. So you actually form small clusters, and then when you have more of these small clusters, the idea was that you also get more of these cloud condensation nuclei. So the next thing is that if you have cloud condensation nuclei, and if you can change them, you are changing cloud properties. And this is something you can see in this. This is actually from Metrosat, I think, from a geostationary satellite. And it's all the same Dave you see, but you can see here what we call ship tracks, where a ship is sailing along. You have a region where you have low clouds. And you see that in the exhaust from the ships, they actually pump out cloud condensation nuclei. And by changing the cloud condensation nuclei, you see that the clouds get much more white, and that means that they reflect much more sunlight out to space again. And that it is an indication that if you change the cloud condensation nuclei, and if you can do it systematically by solar activity, then it will be important for changes in climate. And that was the fundamental idea we had. And over many years, we have been doing experiments. The first picture here, that's our experiment in DTU in Copenhagen. Here it's another experiment we did where we were at the University of Aarhus, where they had an accelerator. So we tested, the effect of having very high energy particles. Here we are using gamma rays. And finally, we had an experiment where we were 1.1 kilometer underground. And the reason why we go so far below ground was to exclude cosmic rays from the experiment. So we had complete control over this situation. So all these experiments that we have been doing in some form or another, they all confirm that when we increase the ionization, so we increase the ionization by gamma rays, for instance, then we can measure the number of small aerosols that are nucleated. So, and we see that as we increase the ionization, we actually get more of these small aerosol particles. So the cosmic rays are really helping stabilizing and helping the nucleation of small particles. The figure over here is actually showing the ratio of, here I have a very high sulfuric acid concentration compared to what you have in the atmosphere. And when you have a high sulfuric acid concentration, the particles don't care whether they're ions or not, they stick together by themselves. But as we go down in sulfuric acid concentration, then the importance of ions increases. And you see that here, for a certain ionization, the nucleation is, from ions is actually 5 times larger than the nucleation that you get at high sulfuric acid. And if we move to the very low sulfuric acid, which we have in the atmosphere, it means that nearly all nucleation is happening on ions. So ions are extremely important for this nucleation. So we can show experimentally that ions are extremely important. The big problem, the next question, which at first I didn't thought was a problem, is that when you have this small nucleated particle, it has to grow to cloud condensation nuclei. And the mass has to increase almost a factor of 1 million. So the growth process here is extremely important, because when the particle is very small, it cannot affect clouds. It has to have a certain size. So there were several groups that started to look into this problem, and what they did was that they used global circulation models to test these ideas. So what they did was that they had a global climate model, and then they injected very small particles on the order of 1 nanometer, and they increased the number of about 5%. So it corresponds to the increase in nucleation that you have over a solar cycle. So because of the increase over the solar cycle, you get about 5% more particles. And then they look at how the particles grow. So they injected an additional amount of particles, but then they see that as the particles grow, fewer and fewer survives. So in the model, when they get to the sizes of the cloud condensation nuclei, the number of particles that have survived is so small that it's irrelevant. And that would be a big problem for the theory, because in order to explain the changes we see in clouds, we would expect that the particles would grow and the number would keep more or less constant, so that we could change the number of cloud condensation nuclei by a few percent. And that would explain our results. So around 2011, 2009, the community was saying that modeling says no to an effect of ions on cloud condensation nuclei. And that has sort of been the idea ever since, that climate modeling actually proves that this idea does not work. And if true, it is, of course, the end of the theory. It's a really serious problem, and I should say it's serious because we have actually spent more than 4 years trying to figure out what is going on. One of the first things we did was, instead of using climate models, was to try to test it experimentally. So in our chamber, we injected neutral particles, neutral very small aerosols into our chamber. So we increased the number by here, 30 or 40%. And then we looked at how they grew towards cloud condensation nuclei. And in this experiment, we have no ionization. So what you see is that, in complete agreement with the models, we don't get cloud condensation nuclei. So even though we put it in more particles in the end, no more particles comes out. And the reason is that when you put in more particles, you have more particles competing for the same amount of material that they have to grow from. That means that they are growing slower. If they grow slower, there's a bigger chance for them to get lost. So this is complete agreement with the models. But if we repeat the experiment where instead of injecting neutral particles, we are producing the particles by ions, and we have ionization in the chamber all the time, then look at this result. So we inject the small particles, and then we see that all the particles are growing into cloud condensation nuclei. So this completely contradicts the model results. There is some mechanism going on, which we have spent several years trying to understand, why it is. This was published around 2012, and it did make some of the modelers slightly uncomfortable that we got these results. But they I think they forgot about it, and they dismissed it, saying that, this going on in the real atmosphere might be slightly different. And therefore, it's very convenient that we could also test these ideas in the real atmosphere. So what you see here is solar activity on a very short, this is from day to day, where you have these explosions from the sun, where you have some plasma that is thrown out. And if this plasma hits the Earth, it can get the cosmic rays to drop within hours, and then over a week or so, it sort of recovers as this plasma moves out through the planets. And this is the figure that Nia also showed, where you see that, I mean, the good thing is that we have these drop in the cosmic rays. Here you have day 0, you have 15 days before the minimum in the cosmic rays, and here you have 20 days after. And what we do is we take the 5 strongest Phobos decreases, and when these minima happens, you can say that it makes an experiment with the whole Earth. And by testing with all kinds of observational systems, we can then look for an effect in aerosols and clouds. And you see a very clear effect in the aerosols. You see an effect here in liquid water clouds. This is also liquid cloud fraction. In the MODIS data, these are all different satellite data sets. They are not even the same Phobos decreases because they are operating in slightly different times between, I think, 83 and 2007. And you also see it in the ISKIP low cloud data set. Now, this was published in 2009, and just last year, we published a very large paper on this whole problem, where we went through all the details, and Nia is also part of this work, but I'm not showing it because there's so much detail in it. But it all points to the fact that it can be explained by changes in cosmic rays. So what it means is that there is a mechanism that links cosmic rays to changes in cloud cover. And then we have all the correlations. I mean, it has the right size, and it links to the cloud cover, and we see all the correlations with climate. So it is a very good candidate of explaining what we are seeing. All the changes we have seen up until this point has been changes in cosmic rays caused by the solar activity. But an independent check is, of course, when you have changes which are caused by nothing, something that has nothing to do with solar activity, but has to do with changes in the source of cosmic rays, which has to do with the star formation rate. So star formation can change the cosmic rays by not 10%, but by about 300%. And this is what you see here. We had solar modulation of 10%, but stellar processes can give you about 100%. And if we test, I mean, the changes on the order of a 100%, you can see here, it's sort of a schematic, but you have to imagine that a star is going through this solar, or this is the Milky Way, and you actually go in and out of regions where you have more star formation. So all these red, points that you see here is supposed to be supernovas going off. And if you are, if the solar system is in such a region, you have much more cosmic rays, meaning that you should have a colder climate. Whereas if you are in between the spiral arms, you will have a warmer climate because there's less cosmic rays. And just to make just a few more notes on this, this is a reconstruction of the supernova rate over the last 500 million years. And you see there are some variations. And you can see that the variations are actually on the order of 300%. So if I now compare this, for instance, I mean, Nia showed you that there are big effects on climate. If I compare this with the conditions for life, and you can do that by looking at what we call carbon-13. Carbon-13 is very important in the sense that if you have biological material and you have life, then you would rather have an uptake of carbon-12 instead of carbon-13. It means if you have a large biosphere, then more carbon-12 from the ocean is stored in the living material, and then you will have more carbon-13. So by looking at how much carbon-13 there is in the oceans as a function of time, you actually have an idea of how the biological system is doing as a function of time. And if I compare these two, because we can do that, because from geology you have these very long time series, you get a result that looks something like this. And you see that, one is the change in the star formation, that is, it has to do with the Milky Way, and the other is actually the conditions that you've had for life over this time, over the last 500 million years. And you see this remarkable correlation. Okay, let me end by giving you a short summary of what I've been saying, that it looks as if, we have very good evidence that, change in star formation and thereby the supernova rate, it changes the cosmic rays. This is not really controversial. But what we have shown experimentally, and we have even from observations in the atmosphere, that these changes are important for the nucleation, and I don't think that is controversial from any point. The problem that we have had, and which we have been really working on for the last 4 years, is this part, the growth of aerosols, so they can become cloud condensation nuclei. And we have so much empirical evidence that indicate that we are changing the cloud cover, and the cloud cover has the right size, so it could explain why climate is changing the way it has been doing, not just from days, but from days out to millions of years. So it looks as if we have a link which connects cosmic rays with clouds and climate. Thank you very much.